Lab6 is all about LabVIEW and programmable devices. So one of the advantages of LabVIEW is that it has the ability to communicate with devices that are programmable, and you can also control them and automate your experiment, which would make your the overall experimental setup a very autonomous, and it makes your experiment faster, efficient, and accurate. So in this course for this fall 2020, we are using the analog discovery 2 from the Digilent. But earlier we were using the Rigol multimeter, function generator, oscilloscope. So those are also programmable. Like I think in most of the labs, like you have dealt with like a multimeter or an oscilloscope and a function generator, but you were controlling it manually. But you can also control them through LabVIEW and make the process automated. So yeah, so but and this fall semester, because of the COVID situation, we decided to use Analog Discovery Toolkit, and it's an FPGA board, and you can implement a voltmeter or a function generator, oscilloscope, and various other functionalities you can implement it using LabVIEW. And the point to be noted here is that AD2 does not have an ammeter. So you can program it to work as a voltmeter, but you don't have an onboard ammeter. So you have to measure the current indirectly. That is by measuring the voltage and then applying the Ohm's law, or based on whatever device you're using, linear or non-linear. So you can find out the current that is flowing through it. So that would be an indirect process. So for Lab6, our objective is to create a virtual instrument to configure and control function generator and oscilloscope. Our function generator will be providing some stimulus, some kind of signal, and we are going to read it with the oscilloscope. So that's the objective of this Lab6. So just make sure you have all the equipment that you need here. I have mentioned here in this lab manual, and make sure you have the Digilent Waveforms VI installed. Okay, so let's get started with this. We begin with the front panel. So I'm going to drop a waveform graph. Okay. This is to show the simulated signal from the function generator. Okay. Or in simple words, if I say that this will show me the output of the function generator. And then I am going to draw another waveform graph, and this is for my oscilloscope. And this will be showing me the signals that are being received and read by my oscilloscope. And then I also wish to have some sort of a control to turn my device on. So for that, I will be choosing a push button to start the device. And I'll label it as start. And then I would also want to have something to stop my device. There you go. Just going to enlarge this. So let's change the label for this. It's going to be my function generator, fgen in short. And this is going to be my mixed signal oscilloscope. So I'm just going to write it as MSO in short. Okay, now we need to, this is going to be on my front panel. Now I need to build the code. So I'm going to the block diagram. Okay, I have these two here. Let me just put this on a corner. So let's see our manual. So to implement any kind of thing like function generator or an oscilloscope, you have certain blocks to building blocks to implement that a device on an FPGA. So we have first we are going to initialize the fgen. We have a dedicated sub VI that performs this function, that is initializing the device. And what it does, it establishes the communication with your device, and it allocates resources that are needed to perform that operation. And then you have the run enable fgen that will transition your session. If it is in a stop mode, then it will make it running. And then you have the configuring step, wherein you have to, you can set the values of the duty cycle, the amplitude, what kind of signal do you want. Do you want to the function generator to give you a DC signal, or a sine wave, or a triangular wave, or a sawtooth wave? So you can do all those settings in this step. And the last step is to close the function generator. So as it closes the session, it stops the communication between your device and between your device and the LabVIEW, and it deallocates any kind of resources that were used for this session. So these are the essential steps, and you don't have to worry about, okay, how about each step. You have a dedicated default VIs that are provided by the Digilent. So you can just use them. So the way you can access those VIs is by going to, so because you have installed the VI package manager, you install that to get access to these VIs. So if that package is not installed, um, uh, not the VI package manager, essentially the Digilent waveforms package. If you install them, they have this default inbuilt sub VIs that performs your functions like initialization, configuring, and closing your device. So it's something similar to your Lab5, how you were doing like this task of writing to a file and reading from a file. So you had a certain procedure for that. So you open a file, you write or read, and then you close that file. So similarly is the case with our AD2. So we go to measurement input output in the functions palette, go to Digilent waveform VI, and then choose, okay, you can just spin this. Yeah. So use function generator, and then you drop the initialize sub VI, and the next step would be run. The next one would be to configure, and this one would be to close. Okay. Okay, I'm just going to place them in one side. Right now, I'm just going to focus on these. Okay. So now we are going to connect them. You can see that instrument handle out should be connected to instrument handle in. And if you want to know more about each of the sub VI, you can just do that by uh, taking the help option. Just click on this and you can read about it, see the detailed help. Okay. This is a part of your homework that you should like go through this in detail. I'm not going through it because that is a part of your homework, and it's a part of your report to I'm just going to give you a brief idea of what the sub-VI is doing in this lecture. So you can learn about different terminals here and what this each sub-VI is doing, what is its purpose. And as you can see that it has different terminals, and there's instrument handle out, and that would be connected to the instrument handle in of the next sub-VI. So instrument handle out is the reference to the instrument. So each session has some kind of probably each session, it has a certain session number, kind of a unique identification number of that session that is being passed on. So that's what I understood. But if you happen to read some more and write about it in the report, that would be good. So it's not mandatory, but you can get some extra bonus point based on your, how clearly you're able to explain things in your report. So that's kind of, so instrument handle out is kind of like a reference, unique identification or text or a number that is being passed on, and that is specific to each session. Okay, then you can then read about the configure part or the run VI part, and then fgen close. You can read about each of them. So I'm going to close this. I'm just going to simply connect them. Error in, error out. Device name. Create constant. And you're going to write it as analog discovery. What else do we have here? Okay, channel. Which channel you're going to use. So create constant and write it as fgen. I'm going to use my first channel. So I'm going to write it as fgen over 1. And reset. You can also have like a button for reset. Sometimes, your the port is occupied, and you might have you might have experienced that with other microcontroller devices like Arduino. Sometimes you have to like disconnect your USB device and then reconnect. So similarly is with AD2. So you can use a reset button, and also if it is still not working, then you can just disconnect your USB device and then reconnect it. So I'm going to create a control for this. So you'll be able to reset whenever you want. Okay, and one thing I just forgot to mention is the the waveform generation, like the initialization VI and the close VI. These two can be run. We can run it just once. You can't run it like multiple times. What I mean is, like, if you want your program, now that the way I have written this code, it will just read once the signal. But if you want your program to run continuously, and you're able to manipulate, like you're able to change, you need to have that option of like changing the signal and just observing the output. So in order to be able to do that, we need to have a while loop. Like you want uh, the program to run continuously. So in that case, the initialize and the close VI, it should be always be placed outside of the loop, not inside of the loop. Okay. So when I do this, you'll be able to understand it. The next step is to create to connect these terminals with either a control and indicator. The way you do is just right click and then say create control. Of course, not constant, because you should be able to change them. And then can create a control for the amplitude. And what else do we have? When you hover over this, you can see all the terminals. And this is so easy. Like you can just do a right click and create control. Don't have to do anything difficult. Create control. For the duty cycles, we are going to create a control. Okay. Now what? Okay. I don't have any errors. Okay. And so there's no way you're using a display. So even if I run this program, for example, you won't be able to see any kind of output, right? We are going to give the values for the amplitude, frequency, duty cycle from the front panel, but we haven't connected this anywhere because we don't see the output option. So in this case, what we can do is, okay, let me just show you. Let's run this and show you. Okay, I've set the amplitude. You can just change it from here. Click, click, change it from here. Okay. Or just choose different values. So when I run this, I get like, it's just running continuously, but there's no output here, right? So, and there's no control to, I haven't used the stop button yet in my program. So I'm just gonna stop from here. So you see that we can't see the signal. So of course it's being generated. Our waveform generator is implemented on the FPGA, but we are not able to see the signals. So one way that we can see that is by using the simulate signal option. Okay, then so you go to express VIs and choose the option simulate signal. Okay. So when I drop this, you have this option of changing different signals and setting up the sample rate. So I'm just going to set this as, okay, I don't remember what's the sampling rate, but you can look up online what it is. So I'm just going to set it to 100,000. Okay. And this is sine wave, and okay, I've set the sample rate and say okay. Okay. And I'm going to drop a case structure here. By default, it will show me Boolean, but okay, before proceeding there, like, let me go and show you this. one, that is the waveform function terminal. This control is of ring type. No. Properties, yeah. So it's a ring type control. So what I mean by ring type control is, it has this property of displaying different options. Like for example, oh, here you go. So it has like sine, square, triangle, or ramp, or DC. So it has some values associated with it. You can either insert another row or a corresponding value if you wish to, or if you want to delete or you want to reorder them, you can do it. Okay. So let's see on the front panel how this looks like. So yeah, this one. Yeah, so it shows like different signal types. And based on that, I'm going to connect this here. So this is, I've connected it to the selector terminal. Okay, so it will select the case. So the first one, I think, how many cases does? Okay, this is by default. So I can just, like write here as sine, default case. You should see the order. What's okay? Sorry. Properties. Let me close this. Okay, sine is 0, right? So that's, you have to write sine here. And the next is square, and the next is triangle and DC. So you should have the same order because this is your selector terminal. So you should maintain the same order in your case structure. Just gonna close this now. In this, you are going to have the second case would be of a square. Let's remove the one. Okay. Then right click and add case after. After this, I think we had a triangle wave. And then again do a right click and add case after. And this we are going to add DC. Okay, so we have made a case structure. And since I am in the square case, I want the signal to be, the simulated signal to be a square. So for that, you just go here and change it to square. Okay. Now, just gonna copy paste, Control C, Control V. So this is my thing here. So it should be sine. So I'm just gonna double click it and choose sine. Oh yeah, okay, has this. Okay, sine, square. So now I have to change it to triangle. Okay. I'm to paste here in this case as well. And this is going to be, let me change it to DC. Okay. Yeah. Now we usually make mistakes here while we are doing this part. So make sure for each case you have to connect the terminals. Okay, so we want to give it the offset value. Basically, we want to read the parameters we are passing to our AD2. So I'm just going to connect these terminals to the terminals of the controls of our function generator. So this goes to offset. Now this is a frequency terminal, so I want to connect it to frequency. Okay. Yeah. The next one, okay, frequency is done, then the amplitude. Okay. See, amplitude wiring is blinking, so just that means I have to connect it to this wire. So just click it. Phase, okay, don't have to give a connect anything. Okay. And the output signal should be connected to our function generator display that we have created, the waveform graph just connected here. So it's like an empty box here, but once you connect, like for each case, the output, then it turns into like, it fills it with the, it's no longer an empty box, it's like filled with blue color. Offset, again, I'm connected here. Frequency, amplitude, phase, no, duty cycle. Yep, just gonna connect it here. Okay, done with case 2. Offset, frequency, amplitude, phase, no, output. Offset, error, output. Now you see. Okay, that means all the outputs of each of the cases is connected to our display, to our indicator. Okay. Yep. Now, why do I have a broken arrow? Yes, structure selector values have wrong type. Okay, so I see that it's red in color. Probably you should just replace it with 0, 1, 2. Okay, you need to make one of the cases as a default case. So that's why it was showing me the error. So, okay, this is done. So this waveform function, the control is of ring type. And as I have shown you in the properties, now each of those sine triangle, they have assigned a certain value to it, 0, 1, 2, 3. So once you connect it to a to a case structure, you should use those values that were assigned to each of those signals and not the name of the signal itself. So because I think it still comes under the ring type, it still comes under the numeric type. It's not a string data type for that reason. Okay, then just let me close this. So we'll rearrange this. Just rearranging these. Okay. Now with these, like properties, let's see if we are able to see the signal. Yeah. So yeah, we are able to see it. Ooh. Now see, like when I want to like change the, the signal, I'm not seeing that effect here, right? Okay, let me just run this. Now that I have changed to triangle, when I run this, okay, I can see the triangular wave. Let's make it 100 so we are able to see it. So I don't see that immediate effect. I'm changing the parameters, but I'm not seeing the change here. So every time I need to keep pressing run, right? And if so, yeah, so it just run once. Now I want it to run continuously, and I want it to change the signal. Like for example, if I'm transitioning from triangle to a DC signal, it should reflect here, not like me running it every time. So that's not an automated process anymore. It's just like a manual process. So in order to do that, we have to use a while loop. That's why we'll be using a while loop. drop it here. Like I said, this portion will run continuously, like because we are changing these values here, but not the, we don't want this to run continuously, this or this. Just gonna make it as last value. Um, yeah, sorry. I'm going to replace it with tunnels, but you can have like a shift register for the errors. Um, I'm not sure right now as of like why you cannot, like there is something to experiment which you can just use a shift register and see if you're able to get an output. That's something that I have not experimented. So because my understanding is because you're just passing the instrument handle in, you don't need to like make a shift register, use a shift register. It's not a data value that we have to store essentially. So just set it to last value, but you are free to, experiment a little on that. Okay. Now I'm just gonna connect the stop button here to this. It's gonna give me a good control. Okay, what about my start button? So if I want to control the start, I'm just gonna use a case structure again, and I'm going to cover all of this. Just gonna put the stop here. Okay. And I am going to connect the start here. So in true case, this is supposed to be executed. Our function generator is supposed to turn on in the run mode. And if our function generator is not started, then what do we want it to do? So in the false case, nothing, you can just leave it. Can we just leave it blank? Okay, so you have a missing assignment to the terminal. Yeah, we can't just leave it like that. So just go to the measurement input output vigilant VIs and go to function generator, and then you can just choose from the utility stop. So this will stop your session. Okay, good. Okay, if we don't start it, then let's see what happens. Nothing, right? Even if I change it, no effect. So I'm just going to stop it. Then I'm going to start my function generator and then run it. Can change it to sine. Wow, why is it not showing me the changes? Hmm. So Okay, the reset is on. So probably for that reason, it's not changing the values here. Just turn this reset off now. Okay. Now let's try to change the values. Okay, now I can see the changes. Okay, and I want the DC offset to be 2. Yeah, I can see the signal here. If I wanted to see a triangle, a square, a sine, yep. Let's see the square, you can change the duty cycle. You can see the changes in the signal here. DC offset. And just increase the frequency. Yeah. So we are able to see this is a simulated signal. Okay. But how do we actually know that this does not confirm, however, that is our function generator able to output the values? Because not completely we can confirm with that. Only if you are able to see this signal, whatever is the signal here is being received here, like then we can say that okay, our the function generator and oscilloscope and AD2 is working fine, okay, with LabVIEW. So I'm just going to stop it here. And then now in the second part, we are going to read the response of the oscilloscope. So it would be used in the same diagram. But here. So now for the oscilloscope also, we have the same steps, like you have to initialize, use an initialize sub-vi, close sub-vi outside the while loop, because we don't want it to run like continuously. And then you have configuration set, configuring the channel so that you can do some settings like the so we are going to use sub-VIs for initializing the mixed signal oscilloscope, configuring the channels, and setting the timing of the MSO, run, enable the MSO, read the input of the MSO, and close the MSO in LabVIEW. So we are familiar with initializing and closing. So as you can see with a configure channel, you have options of set like controlling the vertical coupling, the probe attenuation value, the vertical range, and the vertical offset. So you can give your settings, preferable settings for the channel, and configure timing. It configures the basic timing settings of the instrument, such as you can control, set your device to a certain sample rate, or how much time you want the signal to be acquired, and the kind of sampling mode you want to choose. So runway is similar to what we have done for the F-Gen. So it transitions from the stop state to a running state. And with read, we are able to read the input that is given, that is the input of our MSO, and then close it. Let's do the programming for this. And this is also very easy, not too difficult. So I'm just gonna go here, measurement, input, output, digital and VS. I'm just gonna select this and oops. I'm going to pin this because I'm going to use this palette. Initialize. First we're going to configure and then run it. Okay, let me just put read, run. So for my analog channel, I want to configure my channel. So there are two channels, channel 1 and channel 2 for the oscilloscope. So if you want like dual channel, like 2 channels, then you can drop another. Let me show you. Can just drop another, this is for the channel 2, the configuration. So this is for configuring the channel 1. This sub VI configures the channel 2. Okay, and then I'm gonna do the timing. Okay, go back and then just use the close VI. Okay, I'm just gonna close this. Connect this to this. Now similarly for this, we have to give the device name. So you don't have to write it for the second time. Just, wire it to the same string constant. Reset. Okay, this is also, you can connect it here. Enable channel, set it to constant true. You can choose even control, but I don't want to have like additional buttons on my front panel, but you can use it. Create a constant. For my channel 1, it's going to be MSO over 1 for channel 1. Vertical coupling, create constant. Probe attenuation, create constant. Vertical range, create constant. Vertical offset, create constant. Okay, so I would do the same for this one as well. This is my channel 2, so I'm going to create a constant true and create constant. and this is going to be my channel 2, so it's MSO over 2, and then vertical coupling, create constant, probe attenuation, create constant. You can create controls and see how the, with each of this terminal, how is your signal changing. That is something to explore that you can do to get more confidence and comfortable with the with your AD2, and to to know more about how oscilloscope works. So this is a very good opportunity for you. Sample rate, create I would say control. I just want to show you how when we change the sampling rate, how our signal also, you'll be able to see the change and the signal. Wait, okay, what was that? Acquisition time, create constant, sampling mode, create constant. And then coming to our read VI. So the output of this is an analog waveform, which we will be reading. So let me tell you the output of this analog waveform terminal, this portion. As you can see, this is in red color, meaning that it's a cluster type. So it has two arrays. Okay, so the arrays, this array 1 and array 2. So array 1 corresponds to the data from channel 1, and the array 2, the second array, is corresponds to the data that is being read from the channel 2. Okay, so array 1 is indexed as 0 and array 2 is indexed as 1. So if you want to just read the data from one channel, then you can just filter out. You can just remove the, not remove, you can just extract the array 1, array of 0 index using this function. Let me show you. It should just go to the waveform and choose index waveform array. And see, let me read out what does it say exactly. Selects one waveform out of an array of analog or digital waveforms by an array index or channel name. The data types you wire to the waveform array and index inputs, and the data type of the Y component of the analog waveform determine the polymorphic instance to use. So you can see detailed help and probably see some examples about it. So that's the problem. Okay, and then I'm going to put index as create constant, and that is 0. I'm going to read the data on channel 1, and this will be my output. So what I'm trying to do right now is, okay, this MSO, it will, the waveform graph will display the signals from both channel 1 and channel 2 both. Now what I'm doing is I'm just trying to narrow it down to only one channel, like channel 1, and be able to see the value of the frequency and the amplitude. Like it should be automatically detect. Okay, one thing is we can just see visually from here, like, okay, this is the amplitude 3, like if we can just see visually from here, but I want some kind of display that shows what's the frequency of my signal that's going to be here. So it should show me what is the amplitude, what's the frequency. So for that, I going to do this. Just going to use this VI that specifically measures the amplitude and the frequency of the signal. Not in the express VI, signal processing, waveform measure, and extract tone. So this will take the input signal, measure its amplitude and frequency, and then display it. Okay, error in, error out. And then I want to have some kind of, yeah, I want to have some kind of indicator here. Detected frequency. Create indicator. Detected amplitude. Yeah, that's what we are trying to detect. Phase, oh, it's not important. Similarly for channel 2 also, you can, just copy paste this portion and connect it here, and you can read the detected frequency and amplitude from channel 2. So right now I'm just not going to focus much on it, but you can try that. Oh, I see I'm getting some errors here. Most probably it should be because of we haven't connected anything in the false case when we don't turn it on. So I'm just gonna go here, measurement input output, MSO, utility, stop. Still show errors. Oh, I haven't connected create constant. Okay, one of the terminals wasn't connected, so it was showing me some error. So let's go to our front panel, and we have to like really arrange this. This is my input. These are going to be my outputs. Here for my oscilloscope. Okay, now let's run this, have everything in place. I should be able to see a signal here. Oh, wait, what? I'm not able to see that. So I need to check my connections. Um, why am I not getting the signals here? Okay. Yeah, I just it wasn't running because my connection, apparently my Flywire thing, it came out of the AD2 board. So that's why I wasn't able to see the signals. But yeah, so one of if you don't see any errors here, as long as you have like all your functional blocks like initialize, subvi, close, all this in place, the run and the read, everything in place, and then you have like put the appropriate control indicators and constant, and you're confident about your code, I think mostly it would be because of the connection issue. uh, Either you have not connected or made the proper connections, or sometimes your port gets busy, the USB port, just you need to plug it in and then reconnect it after 10 seconds. So that solves the issue. So that's how I fixed my thing. Like I just had a connection issue, electrical connections. So just I'm able to see the signal here. Let's bring this down to 100. Okay, I'm able to see this, and amplitude is 3. Stop. So let me change the duty cycle. Yeah, I wonder why I'm not getting the 3 here. So what I did is I just changed the pre-trigger value, like I reduced it to 0.01, and I set the vertical range number from instead of 1 I have put as 100. So now I just saw that I'm able to see like 3 value 3, that amplitude. um Yeah, the offset is 0 and the duty cycle is 50. So sometimes the reason why we get like a different, you must be getting like a square signal, but there is a different amplitude or frequency. It could be because of the settings as well. So um, just try to, play around with the values here in the channel settings, and yeah, so probably try to use the run VI after we have used the read function. Read VI, just put it here. This is something like you can try to explore. Just use this run sub VI after the read sub VI, or just use it like outside the loop. Just see how it works like. So I haven't tried that, but you can try that. Okay. And so I just changed it, and I'm now able to see the same amplitude that I'm giving the function generator that value. So if I change the offset, let's say to 1. Yeah, so I can see that it's being offsetted by 1 volt. Okay, let me get this. Yeah, amplitude is 1 and then offset by 1. Okay, I'm able to see that, and then sine, yes. And then it's showing me it's displaying the detected frequency as well. So that's good. And amplitude is 1. Okay, it's showing me that. What if I change it to 2? Yeah, it's showing me detected amplitude and frequency. Okay. 3, yes, it is showing me that also. Now, what if I change this to square? I don't see a correct detected amplitude value. So I can see that it is 1 like visually, but here, although the frequency is being displayed correctly, like if I change it to 1000, I can see the signal here. The detected frequency is correct, but amplitude is slightly more than what I have set in as. Like if I change it to, sorry, triangular. Okay, I have like a smaller value. So for square, you have a slightly higher detected amplitude, and for triangular, you have a slightly lesser value. So I am not able to like figure out like why is it so. Yeah, you can even make like DC and set the offset as, yeah, you can see the DC signal. And this, the red one, is the channel to just like, you can stop this, elongate this, just make it as channel 1. Channel 2. Okay, this would be, if you connect any kind of input to channel 2, you can see it here. So so far we are able to see the changes that are being done here. We are able to see here it's reflecting here, but the only problem that I know of is because it's a DC signal, it's giving us some random value. Okay, ideally it should be giving me 0. Yeah, I wonder why it's giving me this value. But as long as in your the VI that you submit me, I'm able to see the signal here correctly, you're all good. Okay. Here for DC, probably it's not showing me the exact value because it doesn't have like a frequency 0. And for DC signal, probably this VI is not working. Let's read a little more about it. So it takes a signal in, finds a single tone with the highest amplitude or searches a specified frequency range and returns the single tone frequency, amplitude, and phase. The input signal can be real or complex and single channel or multi-channel. So it is going to find out the highest amplitude. So if you have like any kind of noise which has like random peak, it's going to like focus on that. So I'm guessing that should be the issue. But apart from that, you can just try to change different values here of the channel settings and the timing settings, and see if you're able to achieve that. So you are going to get bonus points if you can figure out and what's the issue or find out an alternate solution, or not this VI if you have something else on mind. So you'll get bonus points for that. It's not mandatory, but you will get bonus points for that. So here we have, we conclude our lab 6, okay? And we have built a function generator and an oscilloscope, and we are able to do this stimulus response thing. And just go through the manual, and I have put down the questions that have to be answered in your report. And as I have said you are going to get like bonus points if you are able to, you know, like use a better VI than this, you know, extract single tone information. Just if there's any other way, or if you're able to change different values and fix the issue. Like I have given you a hint right now, like just a while ago, that I wasn't getting probably a proper amplitude, and I changed the pre-trigger value and the vertical range, and then it started working. So you just have to work around with that, and then you can also change the position of the run VI. Either put it here or after this or outside the loop. Just see if it is working, and you can write it down in your report. Okay, so good luck, and we will meet for lab 7. Thanks for listening.